Everyone, and thanks for watching Edupedia World videos. In this video, we move on to the second type of concept in three-dimensional geometry, that is the concept of planes. Just like when we have any 2 points and we join them, we get a line. A plane is formed by the joining of any 3 points which are not collinear, do not belong on a line. And in 2 dimensionals, we saw that the equation of a line in general was of the form y is equal to mx plus c. In 3 dimensions, it was x minus x1 by a is equal to y minus y1 by b is equal to z minus z1 by c is equal to some parameter lambda. The general equation of a plane is generally of the form of ax plus by plus cz plus d is equal to 0. And in this equation you can see, as opposed to the first 2 equations, a particular value of x does not give me a unique value of y and z. If I say take x is equal to 5, then I will get a linear equation in y and z. Something like 2y plus 7z is equal to 6, which would basically be a line in the yz plane. So for lines, the property is a unique value of x gives a unique value of y and a unique value of z. But in planes, a unique value of x gives me a relationship between y and z, which basically would be a line in the yz plane. Right. So another way you can think of it is, what a point is to a line is to a plane. Just like a point is a collection of lines, a line is a collection of points. A plane can be thought of as a collection of lines where all those lines are coplanar. A simple example of a plane would be the xy plane. So if this is x and this is y and this is z, which we won't draw, any line belonging in this plane would be a line in the xy plane. The equation for the xy plane with respect to this format would basically be z is equal to 0. Z is equal to 0 is the equation for the xy plane. Now, for z is equal to 0, you have an infinite collection of points. Just like if you take x is equal to 5, you'll have an equation between y and z which will give me an infinite collection of points. So when you take z is equal to 0, you have an infinite collection of points which would be the xy plane. So our goal will be to find the equation of planes, and we can do it in 3 separate forms. So we need to know the stuff that is needed to be known so that the plane is determined uniquely. Before that, there is one more important thing. Let's say you have a line in this direction. Let's say you have a line in a particular direction. Now we need, let's say, a line perpendicular to this. So that could be this line. But that could also be a line going inside and outside the plane. Something like this, going inside and outside the plane. Right? In fact, any line on this plane would be perpendicular to this line. Right? So when you take a line and you take the collection of lines perpendicular to it, you get a plane. So basically the point is that to every line corresponds a unique plane which is perpendicular to that line. Okay, so if you have, for example, the z-axis, the line perpendicular to the z-axis would be the xy plane. Right? If you have, let's say, the y-axis, this is the y-axis. What is the set of lines perpendicular to y-axis? They would all lie in the xz plane. Right? So to every line there is a corresponding perpendicular plane. There are basically infinite planes. If this would be one plane, a plane parallel to this like this would also be a plane. So if y-axis is the line, then the xz plane would be a plane, but also the plane xz plane shifted by y is equal to 2 would be another plane. Right? The reason this is important is because when we were looking at how to write a line, we saw 2 ways. a point and a direction form or a 2-point form. So, and we'll do something similar for the planes. So for the lines, we had two ways. One was point and direction, and the other was 2 points. Similarly for planes, and I'll write this again in detail, we will have a point and direction sort of, and we will have 3 points, because a plane is uniquely determined if it passes through 3 non-collinear points. And there will be a third way here, which we'll do first. But the important thing is, for a point is generally defined by itself, but for a line, you can define the direction of a line. For a plane, you cannot define the unique direction of a plane, right? If the plane is the xz plane, then there are infinite directions in the xz plane. You do not have any unique direction, but you do have a unique direction perpendicular to this plane, which is the y-axis. So for lines, the direction is denoted by the direction of that line, but for a plane, the direction is denoted by the direction of the line which is perpendicular to that plane. Because for every plane, there is only one line perpendicular to that plane, but there are an infinite amount of lines which are parallel to that plane, which belong in that plane. Right. So that's the first step. So in detail, we'll look at the 3 ways in which a plane is uniquely determined. The first one we'll do first, that's the most general way, but I'll just write all 3 first. The second one would be passing through a point. Plane is uniquely determined if it passes through a point and is perpendicular to a given direction. So there's a reason I wanted to do this, tell you this first before the first point, because this is a fundamental difference not between a line and a plane. There are many differences between them, but this is a fundamental difference between how we choose to give knowledge about lines and planes. For a line, we have one direction in parallel to it, we have infinite directions perpendicular to it. So we choose to give the direction parallel to it. For a plane, we have an infinite directions parallel to it, but we have only one direction perpendicular to it. So obviously, to reduce our effort, we'll give the direction perpendicular to it. And third, passes through 3 points. So we'll do these two, but let's do the first format. A plane is uniquely determined if the following is known. Its distance from the origin, this is sort of an ad hoc thing because the other two are similar to lines, and the reason this is given first is because this relates very directly to the most standard form of a plane, ax plus by plus cz is equal to d. So that is why this is the one which is taught first. If we know the distance of the plane from the origin and the direction perpendicular to the plane, I'll just write it as perpendicular direction. So again, whenever we talk about direction with regards to a plane, it will be the direction perpendicular to the plane because there is only one of that. So a plane is uniquely determined if we know its distance from the origin and a perpendicular direction, or we know that it passes through a given point and is perpendicular to a given direction, or we know that it passes through 3 points. So let's do the first one. We know the distance from the origin. What is the known? Distance from the origin and the perpendicular direction. Just one last time to make clear what the perpendicular direction is. If you have the xy plane, the perpendicular direction is the z-axis. If you have the yz plane, the perpendicular direction is the x-axis. Now once again you can verify that with this marking x, y and z, you do indeed have a right-handed coordinate system. And so it's quite difficult generally to draw a plane. This is how I'll draw it for now. It's not a triangular plane, it's an infinite plane, but this is the way it extends. So basically you take these 3 points. This is a point on the x-axis, a point on the y-axis and a point on the z-axis, and then you join them, and the plane that joins these 3 points, it will be an infinite plane. So that plane is the plane we are talking about. So we know what the perpendicular direction is. So let's say this is the direction n cap, which is perpendicular to the plane. A unit vector given to us to be perpendicular to the plane. And we know the distance from the origin. So let's say this is the origin. Let's say this is the point n where this meets the origin. So n is a point on the plane. The origin is obviously not on the plane because we are talking about this plane which passes through, let's say, the 3 points A, B and C. So we know the direction perpendicular to this plane. There is only one unique direction. We know that in terms of an n unit vector, and also we know the distance between that plane and the origin. Let's say it is d. So these are the two things we know, d and n cap. Now, by the way, n cap, again, the direction can be given in many forms. If it is given to us to be n cap, let's say that is li cap plus mj cap plus nk cap, then we already know that L, M and N are the direction cosines. And if this was instead of a unit vector just a random vector, then these three would be the direction ratios. Right. So we could either be given the direction cosines or we could be given the direction ratios A, B and C, from which you can get L, M and N such that L is A by root A square plus B square plus C square and so on. So this is basically given to us, either the vector or the direction cosines, and also what is given to us is this distance d. So let's take any random point P whose coordinates are x, y, z, and let's denote the position vector OP by R, and let's denote this ON vector by, we can actually write ON vector clearly, that will be d times n cap, because the distance ON is d and the direction is perpendicular to the plane, and this is just r cap. This is just the vector r, which is just the standard variable position xi plus yj plus zk. So what is the property of this? Well, one thing we can see is, since this line ON is perpendicular to the plane, any line on this plane will be perpendicular to this. One line on this plane can be seen to be NP. NP is a vector which can be given as OP minus ON. If this figure is not clear to you, I suggest you draw the figure on your own and look at it properly, because this is important. So NP, this vector can be written as OP minus ON. OP is given to us to be R minus ON. ON is given to us to be D n cap, where D is a number. Now NP, we know for a fact, has to be perpendicular to ON. Since ON is perpendicular to this whole plane, it is perpendicular to any line on this plane. And if you take 2 points on this plane and join them, you'll get a line which belongs in this plane. So NP is perpendicular to ON. What does that give me? R minus D n cap is perpendicular to ON, which is simply D n cap. This is equal to 0. This vector dot this vector. Right. So obviously the magnitude of this is 0. This comes out to be D times R dot n cap minus D squared, because n cap dot n cap is 1. This is equal to 0. D and D cancel, which gives me R dot n cap is equal to D. So this is the final answer. I'll write it here again. R dot n cap is equal to D. Now notice, the only thing we knew was n cap, or the direction cosines from which we can get n cap, and this distance D. Let's say n cap was given to us to be um, I'm thinking of three things which will sum up to be 1. So let's say 1 by root 3 I cap plus, just let's take 1 by root 3 j cap plus 1 by root 3 k cap. These can be direction cosines because L square plus M square plus N square is 1. So this is the vector perpendicular to it, unit vector given to us, and D is given to us, let's say, to be 5. Then we get is R dot n cap. R is xi plus yj plus zk. This dot n cap. So what we get is x by root 3 plus y by root 3 plus z by root 3 is equal to 5. Right. So I'll just rub a little bit of it. I don't want to rub the figure. Yeah, so if we are given that a plane has a distance from the origin equal to d and has the direction cosines lmn or has the perpendicular direction ni plus nj plus nk, then the equation of the vector is simply xl plus ym plus zn is equal to d, or r dot n cap is equal to d. And this is the most standard equation for a plane. That's why this is the form we study first. Now from this we can immediately infer a lot of things. If we are given the plane 2x plus 3y plus, let's say, 6z is equal to 15, then we need to write it in the form of n cap. That's the first thing, right? So what is root of 2 square plus 3 square plus 6 square? So there will be 36 plus 9 is 45, 49, so this is 7. So what we can write it as, this by 7 plus this by 7 plus this by 7 is equal to 15 by 7. The only reason I did this is to make this thing a direction cosine. And so if this is what is given to us, we can immediately see that the perpendicular direction is 2 by 7 I cap plus 3 by 7 j cap plus 6 by 7 k cap. Actually 2i plus 3j plus 6k is also one of the perpendicular directions. Also the distance from the origin of this vector is 15 by 7. Right. If we are given x plus 2y plus z is equal to 6, we can immediately tell that this the perpendicular direction to this vector is I plus 2j plus k. So this vector, so this plane and every line in this plane will be perpendicular to I plus 2j plus k. Now let's look at the second format of the vector. Yeah, let's look at the second format, in which we are given that it passes through a point let's say A with position vector A, and we are given the perpendicular direction. I'll just assume we are given n cap, but we can be given the n vector or the direction cosines or the direction ratio. We know how to calculate the relationship between all four. So let's say we know the plane passes through this point, and this is the perpendicular direction, let's say n cap. Let's say this is given to us to be Li plus Nj plus Nk. Right, this is n cap, and also we are given a point A through which it passes. This is O, this position vector is A. So it passes through OA, sorry, it passes through the point A and it is perpendicular to this direction. Now just for a second notice, if I changed n cap, then this plane would rotate still passing through this point. So neither the point is enough to uniquely determine it, neither n cap. Just as an example, let's say n cap was given to us to be this direction. Then the plane would have been something like this. still passing through this point, but the perpendicular direction would have been this, right? So this is the case. Now we can just take any point R which has coordinates x, y, z. Generally we take it to be P, so I'll just take it to be P, the point P with coordinates R, x, y, z. Now once again we'll use the same trick we used in the previous case. OA vector is given to us to be A, this is known, and OP is equal to R, which is simply xi plus yj plus zk. So what is AP? It is equal to OA minus OP, which can be written as R minus A. Right? So this vector AP is R minus A. Now once again, A belongs to this plane, P belongs to this plane. So the line AP belongs to this plane. And since n cap is perpendicular to this plane, it is perpendicular to every line in this plane, which means AP has to be perpendicular to n cap, which basically tells me R minus A dot n cap is equal to 0. So earlier we had R dot n cap is equal to D, where we knew D and n cap, where n cap was the perpendicular direction and D was the distance from the origin. Now it's R minus A dot n cap is 0, and if this is n cap and A is given to us to be, let's say, x1 I cap plus y1 j cap plus z1 k cap, then this equation would be x minus x1 into n cap. So x minus x1 into L plus y minus y1 into M. I don't know why I did this. M plus z minus z1 into n is equal to 0. This is another form of the equation. Now let's look at the final form of the equation. A plane which passes through 3 given points. Let's say A, B and C with position vectors A, B and C. Let's say we have just 3 points A, B and C, and we need a plane passing through all the 3 points. The 3 points uniquely determine the plane, right? This would be O, this would be A vector, this would be the vector B, this would be the vector C. Let's take any random point P which has the vector R. Now I'm going to take a few points in a particular combination, but you can have many different combinations and finally the answer will come out to be the same. What I'll do is I'll look at 3 lines, the vector BA, the vector CA and the vector PA. So what is BA? That is this vector so this is the BA vector, that is A minus B. Similarly CA is this vector that can be written as A minus C. So now how can we find out the vector that is perpendicular to this plane? Now first look at this, A minus B and A minus C both belong in this plane. So none of them uniquely gives me the vector, but none of them uniquely gives me the plane. But every plane has a corresponding perpendicular direction, which is only one. So how do we get the direction perpendicular to this plane? Well, we only need one. One direction perpendicular to this plane will be the direction perpendicular to both these vectors. That direction will be the cross product of these vectors BA cross CA, which is basically A minus B cross A minus C. So this can be written as n vector. Now this is not necessarily a unit vector, so this will not be the vector in terms of direction cosine. There may be direction ratios. But another thing we know is another vector in this plane is PA, or in this case we'll just write AP, that is OP minus OA, that is equal to R minus A. So now this vector n is perpendicular to this plane. R minus A is this line AP, which is in this plane. They both have to be perpendicular. One is in the plane, the other is perpendicular to the plane. So the final equation I get is R minus A. I'll just rub a little bit and write it at the top. R minus A dot the cross product of two vectors A minus B cross A minus C is equal to 0. Now this is an equation which is satisfied by every point P which belongs in the plane. Therefore this is the final equation. And this equation actually has a much simpler form if we write it in terms of Cartesian coordinates. Let's say A is equal to x1 I cap plus y1 j cap plus z1 k cap. I'll not write B and C, but you know what they will be. B will be x2 I cap plus y2 j cap plus z2 k cap. So in that case, this triple product can actually be written simply as a determinant. A dot B cross C is A1, A2, A3, B1, B2, B3, C1, C2, C3. So R minus A will be x minus x1, y minus y1, z minus z1. And then we'll have A minus B, x1 minus x2, y1 minus y2, z1 minus z2, and then A minus C, x1 minus x3, y1 minus y3, z1 minus z3. And this whole determinant has to be equal to 0. So when you take this, multiply by this, the last two terms are basically just 6 numbers because you know all these values. Here you have, let's say, x minus 3, y minus 2, z minus 1, something like that. So when you do this determinant, you'll again get the equation of the form of alpha x plus beta y plus gamma z plus delta is 0, which will give you the equation of the plane. Now along with these three forms, there is also one more important form which you can get from the equation of the plane. So let's just look at the equation of a plane as ax plus by plus cz plus d is equal to 0. This is the most general equation of a plane, and we can write this as many special formats. One way we can write this is we can say x by small a plus y by small b plus z by small c is equal to 1. Now, in the first case you have 4 independent numbers, in the second case you have 3. But the thing is, obviously, this whole equation could be multiplied by 10 or 20, still you would have the same thing, so the ratios matter. Now, every equation like this, you can actually write this in this form as well. I'll just show you one example. Let's say you have 2x plus 3y plus 4z plus 5 is equal to 0. That gives me 2x plus 3y plus 4z is equal to minus 5. That gives me, so we need minus 1, so divided by minus 5, divided by minus 5, divided by minus 5 is equal to 1. And from that I get x by minus 5 by 2 plus y by minus 5 by 3 plus z by minus 5 by 4 is equal to 1. So you get the point. An equation like this can eventually be written like this. And once you write like this, there's a very important thing which happens. So let's say this is x, y and z. Let's say this is the equation. This is the plane. Right. Now take y is equal to z is equal to 0. Means if y and z are both 0, we get x by a is equal to 1, means x is equal to a. That means the point a comma 0 passes through this plane. But that is a point on the x-axis, so that is this point, a comma 0, which means this length is a. Similarly, if we take x and z both to be 0, we get y by b is equal to 1, means y is equal to b. So this point b comma 0 also passes through the plane where the x and z components are 0, which means this line has a length b and so this line has a length c. Now what are a, b and c? You can already see them because you know what in 2 dimensions y is equal to mx plus c was. C was the y-intercept, and intercept is the point where a line or a plane meets that axis. So if x by a plus y by b plus z by c is equal to 1 is the equation, then a is basically the x-intercept of the plane. B is the y-intercept and c is the z-intercept. So let's say you are told to find the equation of a plane which has the x, y and z intercepts at 2, 3 and 4. Means it passes through 2, 0, 0, 3, 0 and 0, 4. Then the equation would simply be x by 2 plus y by 3 plus z by 4 is equal to 1. So this is one more quick way you can get the equation of a plane, or rather inversely from the equation of a plane you can determine things. From this equation you can immediately determine that x is equal to, that minus 5 by 2 is the x-intercept. But you would have gotten that directly had you put y is equal to z is equal to 0, x is equal to minus 5 by 2. So this is the final form, and whenever you see an equation like this, immediately you should think that maybe intercepts will be involved in this, and a, b and c will be the x, y and z intercepts. So now we've seen how to uniquely determine the equation of a plane given some specific points. In the next video, we'll see a few more properties of planes, such as the angle between two planes, when two lines are coplanar, and so on.